Anyway, so we're very happy to have Wei Wu today. Wei is at New York University, normally based in Shanghai, but this term in New York, and he's reporting on this very interesting work with Paul Dario on the Villain model in 3 dimensions and higher.
Okay. Okay. Thank you so much, Roland, and thanks a lot for the organizers for the invitations. Yes. Okay. I apologize for those of you who have listened to this talk online before. So I'm going to talk about this result about the Villain model. So this is result for a very specific model in statistical mechanics, but it belongs to a larger universality class called the abelian spin models, which there are other examples, clock model, XY model, and the lattice gauge theory, and the U1 group. So they're supposed to be having the same universality behavior. It will be also very interesting to extend what we did to these other cases of models. So just a very high level summarizing. So what our work is actually relies on some of the more classical representations for these U1 valued spin models. Is some kind of, we start with some rigorous Coulomb gas representation, and then doing a renormalization argument and a PDE argument involving the Havre-Sjöstrand representation and homogenization to achieve precise estimates. So let me start with the model. So this is the classical XY model. At every spin, you have so every spin at every site is taking value on the unit circle. So you can write down the interaction potential for that, right? So this is just a simple Gibbs measure, which the energy is the inner product of the nearest neighbor spins. You can also parameterize the circle by the angles. So it gave you beta times the cosines. So this is a very classical models in statistical mechanics. You have studied a lot. It has very interesting behavior, especially in 2 dimensions. So it's been used in modeling for some very interesting materials, the superconductors, for example, so here I'm writing down this measure in the finite volume, but you can also take the infinite volume limit, and it's been known quite some time ago that there is a monotonicity of the measure. These Geneve type of inequalities that can allow you to prove that the spin-spin correlations of the model are monotonic with respect to the size of the system. So there is an well-defined infinite volume limit. So our result will be concerning the infinite volume limit of a very similar type of models. So this is called the Villain model. So basically what's happening is that for the XY model at very low temperature, you would expect that the nearest neighbor angles to be quite aligned with each other, right, in order to minimize the energy. And for that, you can use the following approximation of the e to the beta cosine by this this thing. Okay, so this is still an potential on the angles on the unit circle. It looks like a periodized Gaussian, right? So this is M is like the winding number you're summing over, and you have this Gaussian with these corresponding winding numbers. So this another interpretation of this thing is that this is the heat kernel on the unit circle. So if you start with the XY model and you replace all of these interaction here by this heat kernel, this actually gave you the Villain model. So this is called the Villain model. This is also very interesting and extensively studied model in the literature. It will be very nice to understand large-scale behavior of this Villain model. Now, why are people interested? So maybe I just be very brief on this because these class of models has a very different, very special kind of phase transitions. So often you expect, for example, for the ferromagnetic, that the phase transition is associated with a broken of symmetry, right? So low temperature, you have a broken of symmetry, but this is not true for this class of models, especially in 2 dimensions. There is a Mermin and Wagner type of argument that shows that at every temperature, the continuous symmetry is not broken. So we should possibly understand the phase transition, not in terms of the symmetry breaking, but in terms of the topological defects, namely the vortices of these angles. So this is they actually exhibit the well-known BKT transition. This is something which would be very interesting to establish mathematically. And also in dimensions 3 and higher, a different phenomenon occurs in which you do expect the broken of symmetry. So you have a preferred magnetization, but for these continuous spin models, there is something called the Goldstone mode. So you expect that beyond that, there is a fluctuation given by some kind of a spin wave or a Gaussian free field on top of this broken up symmetry. Now, okay, so what is expected and what is known? So this is a picture not for the X1 and Belay model, but for a very related model of Sine-Gordon model. So for the Belay model, you can think of it's like Z go to an infinity limit there. And so here is the predicted phase transition. Well, it happens for 2-dimensional system. So if you zoom out the scales, you would expect that you would expect that if the temperature is low, then there's some renormalization flow that happening, and eventually that that you flow to a free field, to a Gaussian free field with some effective covariance matrix or diffusivity or some kind of beta effective. So basically, for the low temperature case of the model, they would flow to some free field. But for the high temperature phase of this model, you would expect a mass gap or exponential decay of the correlations. So that happens in 2 dimensions. This here is so this is a free field here, and here is you have a mass gap. Now, what happens in the greater than or equal to 3 is a little bit different. As we said, that at high temperatures, there is this beta critical. So at high temperature, you would expect also a mass gap. At low temperature, you do have a symmetry breaking or long range order. But on top of that, you would expect the Goldstone mode. Okay, so this is the predicted phase diagram, but what was known mathematically was actually, we're still pretty far from understanding the whole picture. The existing results were mostly basically in the 2 extremes, that either were at quite high temperature or at quite low temperature, right? So in this case, we know there is a mass gap. Actually, so both in dimension 2 and 3. So this is the work of Eisenman and Simon. And if your temperature is low enough, then in 2 dimension, there are works of basically of Tom Spencer and co-authors, so McBride and Spencer, and Froelich and Spencer, which gave non-optimal power law upper and lower bound for the spin-spin correlations. It would also be very interesting to make it more precise. In dimension greater than or equal to 3, as we will just explain later, there are results about the existence of the symmetry breaking phase, the long-range order back in the 70s by Froelich, Simon, and Spencer. And basically, what we did with Paul is to show that in the low temperature phase, dimension at least 3, we can have a very precise characterization of the two-point function. Okay, so this is what we're going to report today. Now, so just to be more elaborate on what was known in 3 dimensions, so it's back in the 70s. There is this very nice argument using infrared bound that shows that you have the uniform positivity of the two-point function. As x goes to infinity, the two-point function is bounded below in terms of the 1 over beta times the Green's function, and we know the Green's function is finite in dimensions 3 and higher. So this quantity becomes uniformly positive. Now it will be very nice to have a better understanding of how the two-point function behave. So it actually goes back to much earlier work of, for example, Dyson and Mermin and Wagner, who well, you can do some kind of heuristic Gaussian approximation at low temperature, right? Because if you just expand the cosines, you see that the leading term, well, there's a constant, but then there's a quadratic term. So if you expect that the angle difference are small at very low temperature, then you would expect that you can take maybe a quadratic approximation of your interaction. If you do that, it becomes Gaussian. So for Gaussian model, you can compute everything. In particular, you can compute this how this two-point function behaves. It gave you this answer in terms of the simple random walk Green's functions, which you see that in 2 dimensions, there is this particular power law decay of 1 over 2 pi beta. And in dimensions 3 and higher, you see that the two-point function would have a leading order term, which is a order 1 constant, plus a subleading term, which is of the order 1 over x to the d minus 2, the same order as the covariance of a free field in dimensions 3 and higher. So these approximations, they're giving you the qualitatively correct behavior in 2D and in dimensions 3 and higher, but they're not very quantitatively correct. In particular, the exponent obtained here and the constant appeared for this one and this one are not the right constants. And the reason for that is that by approximating the U1 valued spin model to a Gaussian free field, you actually ignore the occurrence of vortices, right? So there are actually a lot of vortices appearing in the system. Some are positive vortices, some are negative vortices. And what's actually happening is that at very, very low temperature, these vortices and their anti-vortices are sort of tightly binding with each other. So on the large scale, you still see something like a free field, but these things do have some effect which would change your covariance structure for the free field. So it actually, there is some heuristic argument back in the 70s, which I probably won't go through in detail, is that these vortices, they have this argument which shows that the vortices behave like a neutral Coulomb gas, at least in 2 dimensions. Now, and in particular, these they also, in the work of Kosterlitz, this some kind of renormalization flow was carried out based on based on integrating out the Coulomb gas at different scales. So he have this famous equations for the flow, which can tell you that predict the critical temperature of the model to be 8 pi, and this is how the normalization flow should be expected to behave approximately. So these are all very nice works. Now turning to the side of the rigorous mathematical results, so here's a conjecture, is that we said that at low temperature, the two-point spin correlations should have a free field behavior. So this means that if you look at this two-point spin-spin correlation, which is like e to the I theta x minus theta y, it should decay like a power law with some beta effective, which depending on your original beta, but different because of the vortex correction. So this asymptotic power law is so far still remains open in 2 dimensions. Now there are existing works. So first of all, back in the 70s and early 80s, there are works by McBride and Spencer who give the upper bound of the two-point function. And you see from here, this is the Gaussian upper bound, right? This is what you get from a Gaussian free field. And they also get a lower bound at low temperature, which differs from the upper bound. Okay, so let me also mention that there was an improvement of this upper bound by Garban and Sepulveda more recently, but none of these bounds were optimal. Okay, so it would be very interesting to improve our knowledge about this spin correlations in 2 dimensions. There are some related works.
Maybe we should also say 8 pi is not the correct temperature.
Okay, so
well, it's not going to be explicit. But it's not 8 pi. Anyway, it doesn't matter. Sorry.
It's not explicit. Okay.
No, there's no explicit temperature.
I see. Okay. All right. So thanks for the correction. Yes. Okay. So far this is open, and there are some progress in very much related models, not for the XY and Villay model. For example, in the case of the Sine-Gordon and Coulomb gas, which we will see later, it's very much related. There are very nice results by Pierluigi Falco, who actually obtained this power law asymptotics for the model larger than, where temperature is larger than the critical temperature. He also even obtained some asymptotics at the critical temperature as well. This is through this very impressive renormalization group argument. And also there is more recent results by Roland, Park, and Pierre-François. And so they studied a discrete Gaussian model, which is a dual model of the Villay model in 2 dimensions, as we will see later. Discrete Gaussian is just Gaussian free field, but you have your field pinned down on all the integer values. And this model goes through a roughening transition, and it's expected that, okay, if we write beta here, then for large beta, your large scale behavior should be like a free field. So they prove this for the discrete Gaussian model in 2 dimensions. And now, since this discrete Gaussian model is a dual model for the Villay model, it would also be very interesting to see whether there's a way possibly to lead the result for the spin-spin correlation for the Villay model. I guess they didn't have this in their paper because this, if you pass to the dual representation, as we will see later, we will end up with some expectations with respect to this discrete Gaussian, but not with a very nice test function of your field. So this part will be more complicated. It involves highly nonlinear and quite singular kind of test functions. So therefore, this problem is still open in 2 dimensions. Now, coming back to the dimension 3 and higher, this is the conjecture that, if you look at the 2-point function, there is this magnetization squared, and the truncated 2-point function should have this Gaussian behavior, but this effective constant should not be the same as what you did from the Gaussian computation. There will be a correction from all these contribution from vortices. So back in the 80s, there were upper and lower bounds for the 2-point function. For example, using a similar technique of what they did in 2 dimensions, Froelich and Spencer have this upper and lower bound of 2-point function in terms of these Gaussian quantities. And then there is the work at very low temperature for the transversal spin-spin correlations, which is also very nice. So it means that if you look at your system with in some Gibbs state or obtained by fixed boundary conditions, so you can look at your spin-spin correlations in the transverse direction, and upper and lower bound are also being established with the same order, 1 over x to d minus 2, different constants. Okay, so we were able to, with Paul, to establish a very precise asymptotics of this 2-point function in dimension 3 and low temperature. Before mentioning that, we should also mention that there's a sequence of works in Balabans in the 80s and using very elaborate normalization groups and to obtain the correlations for the n vector model, or even for the n component spin models in 2 dimensions, achieving the asymptotics. Okay, these works still seems like a black box to me, that it's very complicated and we did not understand them very well. So what we did with Paul is that we're basically proving this conjecture of the asymptotic 2-point function in dimension 3 and higher at low temperature for the Villay model that we introduced in the beginning. So there is this, in particular, we got this term, which is a constant divided by 1 over x to d minus 2. And this constant is not the same as the constant from the Gaussian case, but a small perturbation of that. So okay, so we managed to see that this is not the same, and we know that this is a small correction to that by exponentially small order. And we're also able to obtain this transversal correlation asymptotics. Basically, we know that the sine of theta 0 sine theta x in this transversal case it converges to a constant divided by x to d minus 2. Okay, so that's basically our result. And yes, okay, so
this gamma function is the free field 2-point function constant, is that right?
Yeah, this is just the free field constant.
The gamma is what you get in the asymptotics of the Green's function, right?
That's right. That's how you get this function. Yes. Right. Okay. So maybe I will spend time talking a little bit in the proof. I guess maybe the audience are coming from more in mathematical physics background. So maybe some of the part I just being more sketchy than the others because a lot of audience know these parts very well. So the strategy is based on the following. So first, we used this rigorous Coulomb gas representation for the model. The Coulomb gas representation is perhaps goes back to the early days of Kadanoff and co-authors, and then it's been made in a rigorous fashion by Froelich and Spencer. Okay, so let's do that. So the goal is to basically give a rigorous statement that you can write the Villay model in terms of a product. You can write the partition function, for example, in terms of a product of a Gaussian free field and a Coulomb gas, because the first part we understand very well. It suffices for us to understand the Coulomb gas part. Okay, how do we do that? So we're in dimension 3 and higher, so there's we have to work with all the differential forms. I'm not going to give into much detail about that, but you can see that there are functions defining on sides or on edges or on faces. So in particular, the vortices we're talking about are all defined on the faces. Now, what we can do with them is that one way to see the duality is to use the so-called Helmholtz-Hodge decompositions, right? So for any vector field, you can write it into a potential field, which is curl-free and plus the divergence-free part. And because this is curl-free, you can also solve what this is. This is, given by some function of the curls. So if we do that, and we start with this partition function for Villain. So here we can just exchange the order of the product and sum. So you sum over all the vector valued m's. Remember, m's are these winding numbers on every edge. So you just first sum of that. And then you can use a Hodge decomposition here, because the sum of m's, you can think of it by first sum of all the m's with the fixed vortices, and then you sum over all the vortices with this divergence equal to 0. And you can use the Hodge decomposition to rewrite the sum in the second part. So this is going to be a potential field plus the divergence free field. Now, the other thing to notice is that they are actually orthogonal decompositions, right? Because this is divergence free. So if you make an inner product, it just disappears. So you can use that to basically decouple the two variables on phi's and on the q's, thanks to the Gaussian nature of the problem. So you have the square here, so it actually exactly decouples. And you can actually combine these angles and this height field together to get an ordinary Gaussian free field. And the second part, you see from integration by parts that this is just a Coulomb gas. Okay, so this is just how this duality works. So you can write your partition function in terms of a Gaussian free field times a Coulomb gas. And so one comment here is that the Coulomb gas has this divergence Q equal to 0 property. So it differs when you're in 2-dimensional or higher dimension. In 2D, this is just a global neutrality condition that your Coulomb gas is globally neutral, and in dimension higher, it's going to be this would actually give you a lot of local cancellations. Okay, which makes the problem somehow easier than 2 dimensions. Now, this is what you did on the partition function level, but you can also do it not just for partition function, but for correlation functions. You get a ratio of the Coulomb gas partition function. It's exactly the same kind of argument where, so this sigma is going to be, you could think of this Coulomb gas with the sigma thing to be, you have a Coulomb gas, but you insert a plus charge at 0 and a minus charge at x. So this is how this this term behaves. You have an extra difference of the Green's functions. So so in particular, because of what was known as the sign-Gordon representation, this Coulomb partition function, it's like a Gaussian integral, right? Because the Gaussian has the covariance Laplacian inverse. So you can write out as a free field expectations like that, or like this when you have this sigma term. So in particular, for example, if you want to improve the upper bound of the McBride and Spencer, you would like to show some kind of variance lower bound for this quantity. So this is basically the work of Christophe Gabin and Abilio did. in 2 dimensions. And now if you want a precise asymptotics of the 2-point function, you basically want to have a precise asymptotics of this Coulomb gas functional, and that will give you a precise asymptotics of the spin-spin correlation function. And then when the temperature is low enough, you can actually do some one-step renormalization. So this we actually learned from notes of Roland, that so just decompose your free field into a local field and a smooth field. So the local field maybe has a covariance something, let's say square root beta times identity. So after doing that, after you integrate out this local Gaussian thing, you see that there's a contraction term look like this. It decays very fast in terms of the norm of your charges Q and with respect to temperature beta. Okay, this is what you obtain after integrating out local field, but then you have to study another integration with respect to the smooth Gaussian field, which is non-local and has long-range interactions. So fortunately, when beta is large enough, this term decays very fast. So you can actually, using the cluster expansion, to resum it and put everything on the exponential. So I'm skipping the details here, but you can basically write it in terms of the 2 ratios of the exponential functionals, taking expectation with respect to the smooth Gaussian thing. Now, another way of writing it is you can write it not in terms of this Gaussian measure, but in terms of the change of measure, right? In terms of the measure with Gaussian plus this term. So you can do that by using these cosine identities, and what you get is the following. So it's a little bit long to display. So basically, the measure changes from the non-local Gaussian measure, which is the phi1 measure here, to the measure which also adding all these perturbation terms. So this is your measure. And on top of the measure, you want to understand this functionals, a lot of sines and cosines. Now, it looks kind of forbidding in the beginning, because we're starting with the 2-point function for the Villain model, and we end up with this huge expectations. But the good thing for us is that this measure, you can see it's log concave, right? Because the leading term is actually this Gaussian free field term. And then there are different higher order terms or perturbation terms, but you would see that as beta gets very big, they're acting like a lower order. So the overall measure is log concave. For log concave measure, we have the tool from Halford-Sillstrom analysis and PDE to be able to say something very precise. So that's what we actually did, and that's why we stay with this dual representation and then carry out some PDE work to give a precise analysis of this asymptotics. Okay, so okay, so far so good. So now maybe for the rest of the time, let me describing how this part of the this PDE argument with input from a quantitative approach of homogenization helps us to study this expectation functional. Now, let's start with a simpler, much simpler setting, just the setting of a convex action gradient type of Gibbs measures. So instead of a Gaussian free field, you can generalize the Gaussian free field by change the quadratic potential to V that is uniformly convex. Here, I mean the second derivative is bounded above and below. Now, for the Gaussian free field, we basically can compute everything. In particular, we know the covariance is just the Green's function for simple random walk or Brownian motions. But there's something quite similar for this gradient functional as well, for this gradient measure. In particular, we have the so-called Helfer-Sjöstrand representation here, which telling you that if I'm looking at under this gradient Gibbs measure, I'm looking at two functions of phi. So they are actually different functionals of phi. Then you can write the covariance in terms of this. So partial x means that taking derivative with respect to phi at x. Partial y is there. And L is an elliptic operator. Okay, so the specific definition of L actually looks like this. So I need to define you what this guy is. So this is something called the Width Laplacian. So the definition is this. So phi x is the derivative to the field. So we have a second order derivative to the phi of partial phi x, but sum over all the x, and we have this term. So it's in some sense an infinite dimensional operator because the x took value in all of the places. And you can see that probabilistically, this is in fact the generator for the Langevin dynamics of your Gibbs measure. And it's therefore you can also check it's a self-adjoint operator if you took the expectation with respect to the original Gibbs measure. So you have this relation, which tells you the self-adjointness. So we have this operator, and we have a usual elliptic operator living on the spatial lattice, which is a ZD, where this diffusivity is given by the second derivative of your potential V. So when the second derivative is bounded above and below, we are happy because this term is just the uniformly elliptic operator in the usual spatial dimension. So it gave us an infinite dimensional elliptic operator. Now let's get back to this Helfer-Sjöstrand representation. A very special case, as we would see, is that if you're just interested in covariance of phi x and phi y, it simply gave you that these two become delta functions. So that just gave you the some kind of the annealed Green's function corresponding to this operator, right? So this whole Helfer-Sjöstrand analysis was, of course, goes back to a work of Helfer and Sjöstrand. And I think Nadav and Spencer were the first to introduce these techniques to the study of Gibbs measures. Now, with that, we could imagine that in order to show some log concave measure, potentially very complicated, behaves asymptotically like a free field, it would be very helpful to be able to see that this averaged Green's function would getting closer and closer to the free field Green's function on large scales. So, here is where the homogenization came in, because the Green's function was solving an infinite dimensional elliptic problem with this operator L, and we see L is very much depending on your random fields, right? All the coefficients there depending on the random fields. So this is a PDE with random field coefficient, and if we can show that the large scale behavior of this problem, or the large scale asymptotics of the solution to this, which is the Green's function, is behaves like the solution to the Green's function to the constant coefficient elliptic PDE, which is well known. So this is simply just the simple random walk Green's function with the diffusivity A bar, and we would be able to conclude this convergence to Gaussian free field. And if we can analyze the rate of convergence to show that this convergence is actually better than than the typical order of the Green's function, then we actually obtain a pretty precise information of how the functionals in the Gibbs measure behaves. Let me give a bit more complicated setting, which is which is a simplification of our setting of Villain model, but looks more complicated. Is that basically approximately we can try to write our expectation arising from the Coulomb gas approximately in terms of something like this, where I'm summing over all the possible charges, and this term G sigma 0x is like a Green's function at 0 minus Green's function at x. Now, you can easily just write it, right, as a part which you only have the Green's function at 0, a part which you only have a Green's function at x, plus their covariance. And by the stationarity, you see the part with G0 and Gx are the same. So in fact, it turns out they're just the magnetization. Okay, these terms correspond to the magnetization part, and then you have this covariance part to analyze. So let me make another simplification, is that at very low temperature, the covariance will be, well, if you want to understand this thing, the charges at low temperature, as we see before, are very much suppressed, right? It's exponentially suppressed in terms of the L2 norm of the charges. So we can assume that the main contribution is coming from just the nearest neighbor pairs of charges. So which means you have these dipoles formed, and you have all this function which only depend on the gradients. Okay, so we can apply Helfer-Strand to study the covariance in this much simpler settings. Now, how did we get? Well, so if you apply Helfer-Strand, you need to take derivative to the term here and to the term there. And what you actually end up with.
Did you linearize the exponential? Or where in the first line, I can't quite follow. So, where does the exponential close? It closes all the way at the end.
Anyway, it's a simplification, and in fact, yes, and in fact, this high order term contribute less. If you look at the covariances.
So you linearize the exponential, is that what you're doing, or?
Well, okay, we actually didn't, but in terms of right. So basically, after this step, so we actually didn't, but it behaves very similarly. So if you apply the Helfer-Strand, you would always have a lot of exponential thing there. But they are, I mean, pretty much bounded functionals and things like that. So, so the short answer is we didn't linearize, but just as a heuristic explanation, I'm storing away all the exponent there. Exponential.
Okay.
Yeah.
Thank you.
So, right. So we can do the Helfer-Strand here, and some of the constant Green's function term, we can just take them out. And we have some very complicated functionals there. We have the e to something here, e to something here, some cosines, but we would gain a double gradient, spatial gradient, for the Helfer-Strand Green's function because of the gradient here and the gradient here. So if we imagine that this double gradient term on the larger scale would behave like a double gradient of a normal simple random Green's function with some effective diffusivity, and we think that give us some leading term, then the rest stuff in this expectation would basically average out to be of some constant order. And so you pick up a leading term, which is like the gradient times double gradient times gradient, and that actually would give you this effective coefficient for the term which is 1 over x to the d minus 2. And if we can show that the convergence they have a rate of convergence such that the second order part is decaying even much faster. You would get some of the estimate on the correction term there. Okay, so so in some sense, in order to nail down this term, we really needed to be able to show that this term is actually much smaller than this order, so that it won't affect the constant there. So, well, this leading to a very similar problem, but we just want to be more precise. We want to show that this Helvetius-Strand Green's function is actually, even if you took double gradient, it's also very close to the double gradient of the homogenized Green's function. So how do we do that? So okay, just a very quick comment that the first work for the homogenization of the Helvetius-Strand equation was done by Naddaff and Spencer, and there were also a parabolic version of that by Giacomi and Spohn. So these works did not quantify the rate of convergence. The first work that quantified, first work quantified the rate of convergence for the Helvetius-Strand equation is in a paper with Scott Armstrong that we wrote, where we used that to study the regularity property of the surface tension of the gradient models. Now, in some sense, both this paper with Scott and the work with Paul, we are following this idea of Armstrong, Kusi, and Murat to study the to obtain a rate of convergence in this homogenization problem for this infinite dimensional elliptic PDEs. And the idea is basically that for elliptic equations, we know that the solution can be characterized by energies. So we just look at the energy functionals, and we do that at every scale, right? So so we're propagating from a smaller scale to larger scales, maybe in some geometric fashions. And for each scale, we have some kind of, we can represent this energy functional quadratically in terms of some effective diffusivity matrix, and try to obtain some iteration of this effective diffusivity matrix when you propagate from a smaller scale to larger scales that gave you the quantified rate of convergence. Now, it turns out that all these energy quantities are somehow approximately subadditive. So you got the existence of the limit pretty much from a soft argument. But in order to get a rate of convergence, it would be actually helpful to have some knowledge of the mixing of the coefficient field. So how does the energy or the solution in one local problem, how does the very far away random field affect your knowledge of the problem locally? So this was actually to date there are quite a few ways of doing that. So I guess the first way to obtain this quantified rate of convergence is by some assumption on the spectral gaps, which was done by Gloria et al., but also was inspired by some previous unpublished note of Naddaff and Spencer. This is somehow related to us, but not quite, because we're doing the infinite volume case and there's no real spectral gap. And then there's also this work along this dynamical coupling that gave you the mixing, which is you couple the systems by looking at Langevin dynamics driven by the same Brownian motion, and then you can estimate the difference of the field under the couplings. So first done by Funaki and Spohn, and then more refined version were done by Jason Miller and also in my previous work with Scott. And what we did is we're looking at the Helvetius-Strand equation with Paul. We look at the Helvetius-Strand equation, and we we differentiate that. So we got some second order Helfer-Sturstrand equation, and we prove a regularity theory of that. So which I will just comment briefly on the next slide. And also there are some other approach that you can do. For example, you want to understand the parabolic problem of random walk in random environment and try to prove regularity of the heap kernel. So that's also there are a few ways that you can try to get the mixing condition and obtain a rate of convergence. Now, so what we did in the Villain case is that we see that the operator is becoming complicated, but you see you can write it as a Laplacian term plus a perturbative term. And as beta go to infinity, this perturbative term will be even smaller comparing to this leading term. So you would expect that on large scales, your solution of your problem is actually can be well approximated by the solution to the problem with just the standard Laplacian, which possesses great regularity property. And in fact, we were able to prove that that we have better and better regularity property when the beta go to infinity. So we got this C0 1 minus epsilon regularity property, which gave you nice decay of the Green's function, the gradient of Green's function. And this improves as beta gets larger and larger. And remember that we eventually want a mixing condition for both the energy functional and the solution for a local problem if you change your field a little bit in some faraway directions. So what we did is to understand, for example, how your Green's function changes if you change your field very far away, you can take a derivative, right? Take a derivative of your Green's function with respect to the field. Now, you obtain another equation of higher order. You see that the leading term of this equation is still Laplacian because you can just pass the partial derivative to inside the Laplacian. But then you got some also very complicated next terms, which I did not write here, which comes, sometimes you pass it through the perturbation operator, sometimes you have a commutation there. But as beta go to infinity, this is still a perturbation to the previous term. So in fact, we can also establish a very strong regularity for the second order equation, which is an equation like that, which can control the decay of your Green's function when you change with respect to the change of the random field at faraway places. And this helps us to obtain the required mixing condition that we need to obtain the quantified rate of convergence. Okay, so that's basically what I would want to say. Maybe I just list the last slide. So there are plenty of open questions that we don't yet know how to do. And some of them are more reachable, right? For example, well, okay, some of them, because the rigorous Coulomb gas representation has been established. So we have some very concrete problem to work with, but it's yet to be carried out very precise argument, either using the PDE argument or using some renormalization to understand the precise correlations, asymptotics in large distance. And also there are problems which is even more vaguely well-defined, and there is some Coulomb gas representation up here in the background, but it's not rigorously established. But also you expect some kind of Gaussian behavior at large distances. So that's, I guess I'll stop here.
Well, thank you very much for this very impressive talk.
Okay, thank you, Roland.
So I suppose maybe there are some questions. Maybe I'll start with one. You mentioned some of the open problems are more reachable than others.
Well,
Um,
okay. I mean,
which ones are reachable, or which ones seem possible,
um,
or at least
okay,
not for.
so they are all, I guess, far from being well understood. Okay, if I make comments, we have this work for the Villain dimensions 3 and higher, right? So, well, a very natural question to ask is what happens for the XY model in the same dimension, right? So you expect the same behavior. The argument doesn't proceed us through directly. I mean, because as you see, when you go to duality, this thing is very specialized to the villain type of interactions. I mean, it might be possible to think of the XY model as a villain model with a random coupling constant. I think there's an argument by Ralphie which does that. If the coupling constant is uniformly elliptic, I believe we can carry through this without problem, but unfortunately it's not. And then there's some subtlety that we didn't quite yet understand. So, I mean, you have this random environment which can only go zero rarely. Do you have the same global large scale property of the model, right? So there must be something very subtle going on, because for X, Y, and for ON, you can also think of it as a villain in a random environment, but they behave differently. So I mean, in a sense, it's kind of one of the cases where it might seem to be more reachable than other, but we don't have much progress though in these directions. And yes, yes, I mean, the short answer is that they seem to be more reachable because there is a concrete problem to work with, but so far they're all open. So
Yeah, thank you.
thank you.
Any other questions?
So can I ask, so when you mentioned this, the critical temperature is not 8 pi, what's the heuristic, like, is there a heuristic description of this?
Well, this 8 pi, it appears in the continuum limit, but if you're on a finite lattice, it's not 8 pi. I mean, basically, there's this effective beta effective, and the critical temperature is where beta effective is 8 pi roughly, but the beta effective is not equal to beta.
I see. Okay, that's yes. Okay.
So beta effective is 8 pi, but it's a function of beta, and it's
yeah. Okay. Sure.
As you drew. So that's where the critical temperature is.
I see. So there's probably there's probably not a nice expression then.
Yeah, I don't think so.
Can I ask a question? Maybe it's naive, but I don't. So at some point you use cluster expansion to represent effective action, no?
Yes.
And then you still need a different argument to establish to control the correlation function.
Okay, so I mean,
why you cannot? Yeah.
So I agree. I mean, in some sense, when temperature is low, you should expect everything is a perturbation of Gaussian, right? So it's you would probably expect that that maybe there's a way involving just using renormalization but not using PD argument. There are some subtleties, I guess, because at every temperature, basically what you get in the limit, you have an effective diffusivity, which is different from the zero temperature case, which is like Gaussian. So at every temperature, I mean, the limit is kind of different and not very explicit. I did not say that you cannot proceed with doing this renormalization group argument. Maybe you can, but I could also imagine it would be also very complicated to carry out because our the function we obtain is also very complicated on the exponent. As you know, with PDE argument, we were not so afraid of this complicated observable here. So that's why we choose to do it using homogenization.
Maybe I can add to clarify. I mean, the way I understood your question is, so this cluster expansion is not, I mean, there's different interpretations of the word cluster expansion. This is not an expansion about a Gaussian measure. The Gaussian measure is still there, and it's a polymer expansion for these activities, but the Gaussian field is still there. It's not integrated out yet. So it's not like a cluster expansion around, as the term is sometimes used in Glim-Jaffe or so.
Okay. So you don't, but how you establish that the polymer decrease then? So how you establish that somehow you can decouple? Maybe I think I was very interested also in his comment. I guess it was my second question, why you don't use one single technique to handle everything. But so this is a polymer expansion, no? Like when you do, for example, to construct effective action, and there is no integration involved. So, I mean, what allow you to do it? So what is the...
I mean,
so what is that make the cluster expansion convergent?
Well, there's this ultra local step that Wei wrote, this very small. So this where you split off an IID part from the Gaussian field, you get a small factor, and then the whole thing can be, you can do the polymer expansion, but it still depends on all of the rest of the Gaussian field.
Okay, yeah. So is this independent variables that? Okay, so the polymer only when they superpose that there is this independent variable which is different from zero. So, I don't know, something like this. Some very local interaction.
Yeah, I think I'm not sure. Maybe Wei can say better, but my impression is that this is only to there's this very local interaction that can be integrated out explicitly. Then you have a lot of small factors in the activities. You can run the polymer expansion, but then this still depends on the main Gaussian field. And to integrate that out, you could try to do this by renormalization group, but that's not what they do. But and they instead use this renormalizing version of the Heffer-Sjöstrand, etc.
Okay, yeah, I get it. Okay.
Yeah, okay, we didn't try that. I mean, in principle, I guess you can try to carry on how this local integration goes with respect to this variable, right? So we're instead switching to the PDE argument. Yes. I mean, I guess you can, because after the first step, you already get a log concave measure. So I suppose you can either flow along what RG gave, and what we did is we do it's like a flow along the homogenization. It should converge to the same thing, I guess. So.
Okay, yeah, I understand. Yeah, thanks.
So is there, can you imagine that this might work in 2 dimensions?
So I guess
what is the main obstacle in 2 dimensions? I mean, I guess I guess the first step is the main obstacle, and then.
Well, I guess here it's I guess from this one to make it work like that, you really need a lot of local cancellation of your cubes, right? I suppose. And yes, so in 2D, we didn't quite get something as nice as this.
And then in 3D, I have another question. Sorry if there's others who also have questions. I was just wondering, in 3D, there's this, I guess there's no, you mentioned on the last slide, the clock model.
Okay. So you want to, okay, so I haven't thought about it for very much. So you want to ask whether there's an intermediate phase or?
Yes, I just remember that there's different opinions of whether the clock model has 1 or 2 phase transitions.
Yeah, so, right. Yeah, so I haven't tried very much on this. Yeah, for large Q, you shouldn't expect much difference, right? So,
well, I don't.
I mean, the clock model, I guess it's the because you well, again, it's not as nice as Villain that you can just expand your Gaussian into 2 parts. So I expect you need a little need some more care and okay, so far it's not very clear to me what to do. I guess maybe XY is somehow more fundamental than clock in this sense.
Yeah. Okay. Thank you. Any other questions? Well, I suppose not. Then thank you very much. And I guess whoever is interested in asking more informally, well, I guess it's already informal, but anyway, we can still continue. Thank you.